solve the curvilinear motion, besides using the rectangular coordinate, we can also use the normal and tangential coordinate. In this coordinate, we let the rho to be the radius of curvature. For example, for the curvilinear motion here, at this point, we can form the arc of circle. Then we can find the radius of curvature from it. And also we can form the tangential direction here, which is ET. This direction is always tangent to the curvilinear path. Tangential direction is the direction for the velocity, and we can form the velocity vector to be VET. The normal direction is always towards the center, and we use the symbol EN for the normal direction. So this is the equation for the acceleration. Acceleration is equal to AN multiplied with the normal direction plus AT multiplied with the tangential direction. In the normal direction, we have the normal acceleration, which can be found by using this equation, v squared over rho. AT is the tangential acceleration, which can be found by using dv over dt. Let's try to form the normal and tangential coordinates at these 3 points. Since the object is moving from A to B and to C, at point A, you know that the velocity is in the tangential direction here, where this direction is tangent to the curvature path here. Different with the rectangular coordinate, where your coordinate is fixed x, y, and z. The normal and tangential coordinate is attached on the object and it moves together with the object. When the object is moving from point A to point B, then you see at point B here, the tangent direction is over here. And from point B to point C, so the point C here, the velocity is in this direction. To find the normal direction, you can form the circle on the curve. For example, at point A, this is the circle that you can form. And you get the normal direction toward the center of the circle. At point B, you can form this circle here. At point C, you have this circle. Then we can find the normal direction from it, which is towards the center of the circle. Let's try with more example. You see at point D here, the path is more curved than the point E here. To find the normal direction for the point D, then you can form the circle from this curve. And doing the same on the point E, then you can form another circle. We observe that when the path is more curved, the smaller circle that you will obtain. So the normal direction is towards the center. So here, toward the center here, you have your normal direction. The length from point D to the center is the radius of curvature 1. Similarly, we can also find the radius of curvature 2 here. When the circle is small, you will obtain smaller radius of curvature as well. So this is the observation when the path is more curved, then you will have a smaller circle. With that, you also obtain smaller radius of curvature. When the path is less curved in this case, then the radius of curvature starts to increase. If you have a straight line here, then to form the circle, you can predict that your circle is very big, up to infinity. You can't form a circle from a straight line, therefore there is no normal direction. In this example, we have 2 scenarios. So you see the arrow here indicate the acceleration vector. The length of the acceleration vector is remain constant at all the points here, therefore the acceleration is constant. This is because the length of the arrow represents the magnitude of the acceleration. However, the direction of the acceleration vector changed from point to point. It was told that the object is moving from point A to point B here, and we need to identify which scenario will experience the increasing speed or reducing speed or constant speed. Since A is moving to the B, so the direction of the movement is over here. You can find the velocity easily, which is tangent to the path here. So don't confuse, the green color is the acceleration vector and the red color is the velocity vector. When you decompose the acceleration vector to the tangential direction here, you observe that the direction of the tangential acceleration is same with the tangential velocity. If the direction of the tangential velocity is positive, then since the direction for the tangential acceleration is the same, it will be positive as well. Imagine that you are driving a car in this direction, so this is your velocity. When you will have positive acceleration, which is in the same direction with the velocity. This happens when you press oil to speed up, so that you experience the acceleration. At the same time, your velocity will increase over time. So for the first case here, from point A to point B, the speed will be increased. By using the same approach on the case 2, we draw the red color to be our velocity vector. So since we are moving from point A to point B, we can find the velocity vector. Then you can project the acceleration vector, which is the green color vector, into the tangential direction. You can observe that the tangential acceleration is always opposite to the tangential velocity in all the points here. So in this case, you have a negative acceleration, which is called the deceleration, where you will cause the velocity to be reduced. So this is like you press the brake to reduce the speed. Therefore, for the case 2 here, you will experience reducing speed moving from point A to point B. Next, you need to identify the point where you have the radius of curvature equal to infinity. To find the radius of curvature, then you need to form the circle in every point here. So for this straight line, we cannot form the circle because the circle is too large up to infinity. Therefore, your rho is infinity. So you obtain the infinity radius of curvature at these 2 points here, which is moving in a straight line. In this problem, the object is moving from the origin O to this point. The curvature path of the object is given by this equation. The speed of the object at this point is 28.8. So we draw in the tangential direction, the velocity is 28.8. And the speed is increasing at 8 meters per second squared. So this is acceleration in the tangential direction. First of all, we need to identify the direction of the velocity. So we know the velocity will be always tangent to the path. So the velocity 28.8 will be in the tangential direction here. So we can form our first equation where you have the velocity vector to be 28.8 in the tangential direction. Next, you need to find the magnitude and the direction of the acceleration. To find the normal direction for this object, then you can imagine a circle on this curve. Let's say this is the center of the circle, so your normal direction is towards the center. So for your acceleration vector, the normal direction is here, and your tangential direction is here. The tangential velocity is given previously, so you can substitute inside here. So you obtain the velocity vector to be this answer, and then this vector is with the theta angle away from the horizontal direction. To find the angle, you need the delta y divided by delta x. So this is tangent angle. When we take the limit for this term, where you have your delta y and delta x approximate to 0, then you obtain dy over dx. So you can find the tangent angle by using dy over dx. Since this formula is given, we can differentiate it to obtain the dy dx here. So after you differentiate 3 over 2 multiplied in front, you have the 3 over 8, which is this. So 3 over 2 minus 1, you obtain 1 over 2. So this is the answer for dy dx. And you know the dy dx is equal to tangent theta. So this object here is 16 meters away from the origin. Therefore, your x is equal to 16. We substitute inside this formula. Substitute 16, then you obtain tangent angle equal to 1.5. Then you should be able to obtain the angle to be 56.3. So this angle is the tangential direction, where the tangential direction is 56.3 degrees from the horizontal at this point. So for the acceleration here, the tangential direction is in the same direction here as well. And for the normal direction, then you need to take 56.3 plus 90 degrees. So this is the angle away from the horizontal, and this is the normal direction. The only unknown is the AN, where later you can find it by using the V square over rho. So we continue with the acceleration part, and previously the tangential acceleration is equal to 8, and your normal acceleration is equal to the V square over rho. The radius of curvature can be found by using this formula. So you need the dy over dx where we get it previously. You can further differentiate the dy over dx to obtain the d square y over dx squared. Then you should get this answer. After calculate this formula, then you should get the rho equal to 125 meter, which means at this point, when you plot a circle at the normal direction here, so from the center to this point is the rho. And this is the radius of this circle, which is equal to 125. Substitute the rho to be this answer, and previously the velocity is equal to 28.8. So after you substitute inside, you should obtain 6.64 for the AN. So you success to obtain the acceleration vector to be this. So for the AN equal to 6.64. So from here to here, you have the AN equal to this. For the tangential acceleration is 8. So over here you have the AT equal to 8. Then you need to find the magnitude of the acceleration, which is the resultant. So A total is equal to taking the square root of the 6.64 square plus 8 square. So this is the magnitude. You can find the direction for the resultant acceleration here by forming a triangle. So you need to take 6.64 divided with the AT, which is 8. So tangent angle is equal to 6.64 divided by 8. So let this to be angle 1, here to be angle 2. So you have your tangent angle 2 equal to 6.64 divided by 8. So to find the angle 2, it will be equal to arctangent. So once you find the angle 2, so the direction for this will be angle 2 plus angle 1. So previously you obtained the angle 1 to be 56.3. So angle 2 is this. And if you calculate this, you obtain the angle to be 96. So you have the resultant acceleration here. The magnitude is equal to this. And the direction is 96 degrees away from the horizontal. You must know the difference between the curvilinear motion and the circular motion. So for the curvilinear motion, we are using the rho to represent our radius of curvature. And you can see by following this curvilinear path, you see from point to point, the radius of curvature change. On the other hand, if the object is moving in a circular motion, then the radius of circle is constant. For these two cases, the formula that we use to compute the velocity and acceleration vector are still the same. The main difference is we replace the rho to be r because we want to indicate the radius is constant for a circle. So please use the symbol carefully. When you have a radius of curvature which can be changed, then you use the rho. When you have the radius of circle that cannot be changed, then you use the r.